All right, hi you guys. So this is going to be our first lesson for Math 20-2. We're starting with Chapter 8, so please just be aware that we're starting not with Chapter 1. And so if you're following the schedule according to what I had posted in the course outline, then you'll be kind of like following along with where the course will be in terms of how lessons will be posted. As well, I'll be making up like unit tests, and so if you're not following the schedule in terms of how you're doing the units, there's a chance that the exam might not be ready when you want it to be, because I'll be making up materials as I go, and they will be in this order that I have posted. So make sure that you're starting with Chapter 8 here so that you're on the same track as the whole class. So we're going to be looking at proportional reasoning in this unit, and so we're going to start out by thinking about what is rate. And so rate is a comparison of two different units, and you might have heard of the term ratio before. You should have definitely actually if you're in Math 20-2. Ratios compare things that have the same units. So like, for example, how many red apples to green apples are there in a bag, right? So we're comparing apples. It's just that one is red and one is green, but the units are the same. Whereas with a rate, we're using two different units. So an example of that would be if you're thinking about how we measure speed, we're comparing distance and time, right? So in this case, distance measured in kilometers, time measured in hours, or price. Prices of food would be a comparison of the cost to the mass of the food, or sometimes the volume. So in this case, we're comparing dollars to kilograms. Now, when you're going to be working with rates, it's important to be able to do conversions. And of course, because we're Canadian, we mostly use metric. And so you should become familiar with how these units kind of are related to each other. So in the middle here we have something called base units. So this would be the units that you have that don't have any prefix, so nothing in front of them. So just a liter, a meter, or a gram. Now, if we have larger versions of these units, then we put in one of these prefixes. There's more prefixes that you could use, but these are the main ones. And actually, kilo is really the main one that you actually really need to know. So you probably recognize like the term kilometer or kilogram, right? And then if we move into smaller units, then these are the prefixes we would use. So for example, centimeter, millimeter, okay, or milliliter is another common one that we would see. And so what you basically need to know is how you're going to change the numbers if you're converting between these different versions of the units. So essentially, like, if you have a liter, or let's make it really easy. Let's say if you have 1,000 liters and you want to know how many kiloliters that is, then basically what happens is, because you're moving from a smaller unit to a bigger unit, you need to divide your value by 10 every time you move a unit over. So essentially, if we start out with 1,000 here, we would divide it by 10, which gives us 100, and then divide it by 10 again, which gives us 10, and then divide it by 10 again, which would give us 1. So we would have 1 kiloliter for every 1,000 liters. Okay, now if you're moving into smaller units, then you need to multiply. So for example, if you have 1 meter and you want to figure out how many centimeters that is, you would divide it by 10, which is going to be down to 0.1, and then divide it by 10 again, which would be 0.01 centimeters. Okay, so 1 meter is 0.01 centimeters. Wait a minute. Actually, that doesn't make sense because it should be 0.1 or did I say 10 centimeters? Oh no, I said, okay, 1 meter. If we go down, it should be, 0.01 of centimeters. Yeah. I was thinking of converting the other way around there. Okay, so essentially you're just going to multiply 1 meter. Oh, that's why, because I was still working with division. That didn't make sense. So multiply by 10 again, so that's going to be 100. There we go, that makes sense. 100 centimeters for every 1 meter. Okay, so there's a bunch of questions here that basically go through that same math. Should be pretty straightforward. You're just doing the same thing, and I've written out here basically how I got these answers. So for example, with this one, because you're moving from liters, which are a smaller unit, into kiloliters, which are a bigger unit, you're dividing by 10 however many times you jump over. If you're familiar with these terms well enough to skip the counting how many times, like if you just know that there's 1,000 kilo units in a base unit, then you can do the conversion directly. By no means do you have to try and do this skip every time. And then same thing going from smaller to bigger. Like a lot of you probably already know, there's 100 centimeters in a meter. And so then you can just use that conversion directly if you're more comfortable with it. But this method that I've shown you here is just counting the skips. Okay, so let's go through some examples where we try to use these conversions to work with rates. So when shopping, Alex does some comparing of prices. He notices at Safeway he can buy sliced ham for $1.09 per 100 grams. And at Superstore he can buy the same ham for $10 per kilogram. How can Alex figure out which store has the better buy? So the important thing with these questions always is to pay attention to the units, right? So we have kilograms here, we have 100 grams here. Now, the easy kind of thing to do here is to first of all convert one or the other of these so that the units of weight are going to be the same, right? Because we already have the same units for cost, they're in dollars. So in this one, I think it's personally easier to convert both of them to the larger unit, to kilograms, because that way you can multiply. Division sometimes tends to be a little bit trickier for some students. So essentially what we would do here is we would say, okay, if this one is $1.09 per 100 grams, and I want it to be this to be in kilograms, then I could say, okay, 100 grams we know is, if we use our conversion system here, is going to be 1, 2, 3 divided by 10 3 times. And so if I do that, I end up with 0.1 kilograms. Okay, now one important thing to be aware of that a lot of students make mistakes with here is we've divided this bottom part by 10 3 times so that we have the equivalent mass in 0.1 kilograms. And some students here would remember that usually if you have a fraction, if you do something to the bottom, you have to do it to the top. That is only accurate if you were actually changing the value of this measurement. And what we did here is all we did was change it into a new unit, but the actual mass is the same. So 0.1 kilograms is equal to 100 grams. And so we don't do the division of 10 3 times with the $1.09 because that would actually be changing the dollar value. Okay, and we'll see that when we move on to the next step here, how that would be different if you're actually changing the value. So your next step is going to be to compare the same sizes of for the rate. So essentially what you would say is, okay, if I have $1.09 per 0.1 of a kilogram, how much is that going to be if I have a total of a kilogram in weight, right? Because that's my other comparison. So I already know at the other store, at Superstore, how much a kilogram weighs. It's $10. So I want to figure out if this one that was 109 per 0.1 of a kilogram, I want to figure out how that compares when it's measured out of a kilogram. You have two options here that you can use. I know that some students really like cross multiplication. I personally don't love it just because it doesn't really help you to understand the math of it. However, if it's something that really helps you out a lot, or if it's something that you're very familiar with that you've used in your learning, then you're free to use it. And so with cross multiplying, essentially what you do is you set up a relationship like this where you have your original ratio here, so the price per 0.1 kilogram, and you set it up as being equal to the mass that you want, which is 1 kilogram, with an unknown dollar amount, right? So that's going to be your X value, and you can solve for that. And so when you cross multiply, basically what you would do is, once you have this comparison of these ratios set up, the two numbers that are diagonal from each other, that you can multiply. So you would multiply them like this, and then you divide them out by the remaining number there. Okay. So like I said, I don't love that because it doesn't actually make you think about what's actually happening. So I prefer that you use proportion. And so basically with proportion, you're doing the same thing. I was going to maybe rewrite it out, but maybe I can explain it here. So if I want to make 0.1 kilograms into 1 kilogram, essentially I need to multiply it by 10, right? Because I need to move this decimal place over by 1. But like I mentioned up here, this is no longer changing it from a unit to another unit, but the mass is staying the same. This is actually changing the mass. 1.1 kilograms is not equal to 1 kilogram. So because I had to multiply that by 10 to make it into 1 kilogram, which is a different mass, these masses aren't equal, that means that I do also have to multiply my top value by 10 in order to keep these ratios equal. So $1.09 multiplied by 10 brings me to $10.90. Okay, and so either one of these methods does end up with the same value, which is basically telling you that for 1 kilogram of mass, you're going to be paying $10.90. And so that was the amount that we found at Safeway. So I should actually be putting in here $10.90 per kilogram is how we would want to write that out. Okay, now that I have my mass, is equal, I can see that $10.90 per kilogram. Sorry guys, my microphone just cut out there. $10.90 per kilogram is obviously more expensive than $10 per kilogram. So then you would always, in your answer, want to put down which is the better buy. So we'd say Superstore is the better buy at $10 per kilogram, which is 90 cents cheaper per kilogram. Okay. All right, let's look at another example. So for a big holiday meal, Grandma Jones decides to buy a turkey. She has a tight budget, so she needs to see how big a turkey she can buy. Sobeys has turkeys on sale for $1.75 per pound, and she thinks she will need a 25-pound turkey, but her budget is only $40, so she has to figure out if she can afford the 25-pound turkey. And so basically we can set up an equivalent ratio like this again. So if the cost is $1.75 for 1 pound, and she thinks she's going to need 25 pounds, then we want to figure out how much, what will that dollar sign be here for the 25 pounds. And so again, personally, I prefer that you use the proportion method, which would basically tell us, okay, if it's $1.75 for 1 pound, well, 25 pounds is not equal to 1 pound. So this isn't a conversion where we're converting between units, but we know that 25 pounds is 25 times greater than 1 pound, right? Because basically if I go 1 times by 25, I get 25 pounds. That means that I can just multiply this cost by 25 to find the price. So $1.75 times by 25 tells me that the total cost for a 25-pound turkey is going to be $43.75. So that means that this turkey is over the budget that she set of $40 by $3.75. Okay, so if she wants to be really careful and stick with her budget, they're asking you what is the maximum size of turkey that she can afford. And so again, you can kind of set this up as equivalent ratios where, again, we still have this same price, $1.75 for 1 pound, but we're saying that it's equal to, she only wants to spend $40 and we need to figure out how many pounds is that. So $40 per how many pounds. So this is where the proportion stuff can be a little bit trickier, because you basically need to, this is when division kind of comes in, which tends to be what more students struggle with. And so what you need to think about is essentially how many times can $1.75 fit into 40, because this is a price per single pound. So if we do 40 divided by $1.75, then we get 22.9. Okay, if you wanted to do the cross multiplication, remember you have to use the equivalent, the numbers that are like diagonal from each other to multiply, and then divide it by whatever number is left over. So in this case, it'd be 1 pound times by 40, and then divide by the only number left in here, because this is x, so it doesn't count, is going to be the $1.75, and you get the same answer of 22.9. Okay, so basically what this is telling us is that you would have 22.9 pounds would be the amount here. So I should probably fill that in here. I didn't put in units when I made these notes. So assuming she can only buy full pounds, right? So imagine that the turkey she can buy, you have to buy it to like a single pound. You can't buy decimal pounds. So the biggest turkey she would be able to afford would be 22 pounds, right? Because that 0.9 wouldn't fit in there. And if you round it up to 23, then she would technically be over budget. Now, of course, in real life, you would probably just spend like the extra couple of cents and get the 23-pound turkey. Okay, so that's looking a little bit at cost and weight in terms of rates. Let's have a look at some examples that include graphs. So while driving through the mountains, Joelle kept track of her distance from Jasper on for the day on the following graph. Okay, so she lives in Jasper. She goes for a day trip driving through the mountains, and here we can see the graph of this trip. So we can use graphs to interpret rates. Basically, we can use exact values by finding how far from Jasper they are or she is and how long it took them to travel that distance. Or we can look at the slope of the line, which is going to give us, if you do the actual calculations, it'll give you like an exact value as well, or you can use it as a general idea. So since you've learned in previous years, not just last year, but hopefully you know from previous years of math, that slope on a graph, so just talk about how much it's going up and down, or up and down basically. The slope is calculated as rise over run. So rise is how much is it going up on the y-axis divided by how much is it going across on the x-axis. So that's your run is going from left to right. And that's exactly what rate is. So even if you think about that, when we measure speed, and we used this as an example when we looked at rate on the previous page, we know that speed is measured in kilometers per hour. Now, they didn't actually put this on this graph, so that's not great, but the unit should be hours there. And so the slope is going to be kilometers per hour, which is exactly showing us that slope is equal to rate. Now, a couple of things to remember when you're interpreting graphs. So basically, the steeper the slope is, the greater the number of kilometers are per hour, right? So essentially, if we compare section A with section C, for example, which one is steeper? Well, we can see right away that C is steeper, right? It goes up over a shorter amount of time. And so what that means is that in less time, this section of the graph is covering more kilometers, right? So you always just want to think about what's going on with the different components of the graph when you're thinking about things like that. So in this section here, it's going to take more time, so more horizontal distance, to go, the same amount of distance, versus here it takes much less time to go the same amount of distance. And so then that we know that that means you're going faster if it takes less time to cover the same distance. So just by looking at the graph, not worrying about specific calculations, when was Joelle going the fastest? Well, we just kind of went over that. That would be section C. When would she be stopped? Well, the only place where you're stopped is where your distance is not changing over time, right? So in section B, there's no change in her distance. It's not going up or down as time is going by. So the flat section is going to be where she is stopped. And then the last section asks you, when was she going home? And this is an important thing to be aware of, is that in section D, we can see this is the only section of the graph where the distance from home is becoming less and less as time goes by. And what does that mean when we think about it? Well, if your distance to home is becoming less, it means you're getting closer and closer to home. So just be aware that when you have these distance time graphs, a change in the direction of the graph like this is not showing you a change in speed, right? Only the slope can show you that, but the change in the direction is only showing you the direction, okay? So in this case, going towards home. All right, let's look at just a couple more questions here, or actually just one more example. So Tina has started running. She decided to run a 5-kilometer race and completed the race in 45 minutes. She then decided to do a really long race. She ran 13 kilometers in 1 hour and 51 minutes. What was her speed in kilometers per hour in each race? So we run into this problem here again that we want to have her speed in units of hours, but in each one of these we have minutes. So in one of them it's just minutes, and in the other one we have a combination of hours and minutes. So we need to make sure that both of our units are set to hours. So in this first section here, I kind of cover both of the races. So 45 minutes. If we want to convert it into just hours, we need to basically make a ratio of how many minutes there are that she took, basically, to how many minutes are in an hour. So 45 minutes out of a total of 60 minutes in an hour. If you do 45 divided by 60, you're going to get 0.75 hours, right? 3/4 of an hour. If we have the hour and 51 minutes, we need to do the 1 hour, but we need to add on the fraction, which is in minutes. So the same calculation here, 51 minutes divided by 60 minutes gives us 0.85 of an hour, and then we add on 1 to that, so 1.85. And you can always think if that makes sense, right? Because most people know like a quarter of an hour, a half an hour, and 3/4 of an hour. They know what those would be, like 15 minutes, 30 minutes, and 45 minutes. So does it make sense that 51 minutes is a little bit over 0.75? Yes, it does. And so now that we have our values of time, we can figure out what her kilometers per hour were. And basically all you have to do there is set it up so that you're saying how many kilometers per hour. When you do something like that, if you have your units already, so we were told that she did 5 kilometers, and you divide it by, you have your units of hours, then you're going to get the speed in kilometers per hour as it is, so you don't have to do any further conversion. Okay, same thing here, 13 kilometers divided by 1.5 hours, and that gives us 7 kilometers per hour. So you can see that she ran a little bit faster in the second race there. All right, so you guys have some work to do here. These are some practice questions that you can try on your own. I've written the answers in there. If you can't figure them out, then let me know, and I can send you a little video of how to solve these last 3 practice questions. And then when you're finished with those, I'd like you to do these questions in the textbook. Those should be a good way for you to kind of solidify your understanding. And I will see you in the next lesson, which will be 8.2.